Hello, in this video, we're continuing our nuclear reactions fun with the math of fission and fusion, the two types of nuclear reactions that we're really dealing with. So here we go, we're gonna talk about both of them. The key concept behind these is another fun, crazy idea called binding energy per nucleon, which is what it sounds like, but it probably sounds crazy. So let's look at what we're talking about. All right, so binding energy, remember, is the amount of energy like holding a nucleus together. So if I have a proton and a neutron stuck together, they're stuck together with a strong nuclear force. It would take some work to pull them apart. That's because there's an energy holding them together, a binding energy. Generally speaking, the bigger a nucleus gets, the more energy is holding it together because there's more pieces. They're all pulling on each other with a strong force. So the binding energy increases with the size of the atom. So we talk about like the beginning of the periodic table with like helium and lithium and stuff, relatively low total binding energy. As you get bigger and bigger and bigger, and there's more and more things, nuclei in your nucleus, nucleons rather in your nucleus, well then there's more binding energy tying that whole thing together. However, the really fun thing is it's not like every proton you add increases the binding energy by the same amount. It's very complicated where this comes from, way beyond what we do. It's got to do with the nuclear configuration and nuclear energy levels and some fun quantum stuff that we'll talk about a little bit. But all you really need to know is that it's not constant. So every nucleus has its own binding energy per nucleon. And so here's how we do that. It's truly just binding energy per nucleon. So you take the total binding energy, the total energy holding any given nucleus together, divided by the number of nucleons, which are protons and neutrons. So total of protons plus neutrons. That tells you the binding energy per nucleon. And the reason that's important is because it tells us a lot about different reactions that can take place. We can graph binding energy per nucleon for all of the different atoms or nuclei that there are. And we get an interesting curve. It's called the binding energy per nucleon curve, and it's a big one. This is like a very, very big deal in nuclear physics. You need to know this beautiful graph. Here it is. All right, so make sure you have this sketch. Sketch it out as best you can, in your notebook. You don't need it to be exact. I don't know that you need the numbers on here, but you do want to know there's a quick increase up to some plateau, and it kind of drops off. So what we have here is binding energy per nucleon. So it would be mega electron volts per nucleon. That part's important. So per proton plus neutron in there. And we get this weird, crazy pattern. And versus nucleon number, so this is the total number of protons and neutrons together. So you can see it increases up to a certain point. That point is iron. Do label this. That's important. Iron, it turns out, has the highest binding energy per nucleon. So the nucleus of an iron atom is held together, on average, stronger than any other nucleus. So iron, it turns out, is very stable, and things will tend to go towards iron when there's nuclear reactions happening. Okay, so this is the most stable nuclei is iron. You just want to know iron is the middle here. Okay, so take a moment, sketch this out, and we'll talk about what the heck is going on here. All right, there's two ways you can move on this graph. One is with fusion, and fusion happens on the left side of the graph before iron. So fusion is, if I say take a hydrogen 2, let's say I take two hydrogen 2s, smash them together to make helium-4, a kind of basic idea of fusion. It's fusing two small nuclei together, and by doing that, if it's small nuclei and I smash them together and make something bigger, energy will come out. Dealing with this graph can be complicated. The easiest thing to remember is if in your reaction you end up moving upwards on the graph, energy will come out and it will want to do that spontaneously. Whereas if you're trying to move down on the graph, if I had a helium nucleus and I was trying to break it apart into two hydrogen 2s, I would have to put energy in to do that. All right, you'll notice then something happens with iron, which is why we have two different regions of the graph and two different types of nuclear reactions. That's the big idea. But the difference in the binding energy is if we think about what we did last time, that's what gets emitted as energy. So let's take an example here. Let's take my let's look at, say, a hydrogen 2. It's got about 1 mega electron volt per nucleon. And there's 2 nucleons, so hydrogen 2 would have a total binding energy of like 2 mega electron volts. Compare that to your helium 4, which has about 7, and there's 4 nucleons. So it's about 7 million electron volts per nucleon, and there's 4 nucleons. That's what this number means. So helium 4 has a total binding energy of 28 million electron volts per nucleon. That's a big difference. And the difference in the total of your products and the total of your reactants, so like 24 here, million electron volts, would be the difference in binding energy. That would be what gets emitted as energy. All right. So you take the difference in total binding energy. That's the delta E in your delta E equals delta MC squared equation. So again, the quick version is if you move upwards on this graph, energy will come out, and things tend to want to do that. So on the left side of the graph here, fusion will naturally happen. If I put any 2 small things together to make something bigger, I move upwards on the graph and energy will come out. So fusion will happen over here. We can look at some kind of examples. Because the graph is really steep over here, there's like a really big increase in energy as you go from really small stuff to slightly bigger stuff. The biggest increase is over here in the low stuff. So fusion, you can get an immense amount of energy out here because the change in height on this graph is really how much energy you get out of a nuclear reaction. And so fusion is where the big energy is. And the main place that fusion happens is in the center of a star. So the sun is constantly fusing hydrogen into helium at this stage in its life cycle. And this is part of the process that's happening. There's multiple different reactions happening inside, but different types of hydrogen are smashing together to form helium, releasing stuff and energy in the form of photons and light. And so we get a ton of energy out of this because, again, we're moving up on that curve. So as I move from like hydrogen 2 and hydrogen 3 to a helium and a neutron, I'm moving way up on the binding energy per nucleon curve. And so that change in total binding energy is what's getting released as energy. The sun is doing a lot of this every second. You don't really need to know any of these numbers. These are just for fun. But this change in mass thing is very real. This also gives you an idea of how big the sun is. So if you crunch the numbers, this is about how much delta M the sun is doing. Every single second, the sun's mass decreases truly by 4.3 billion kilograms because of this fusion. Because again, as you're doing fusion, you're turning mass into energy. Whenever you move up on that binding energy per nucleon graph, from hydrogen to helium, say, in a reaction where you smash hydrogens together to make helium. So I start here, I end up here, I move up on that graph. I'm turning mass into energy. That's what's happening. And the amount of mass that the sun is turning into pure energy every single second is 4.3 billion kilograms. For some kind of sense, the Empire State Building, the actual building, all the metal and glass and stuff of the building is, according to Google, 331 million kilograms. So if we divide, that's about 13 Empire State Buildings worth of mass every second that the sun is just obliterating, annihilating, turning into pure energy. All right, that mass is ceasing to exist and is instead turning into energy. And that is the energy that comes off of the sun. Remember, we get a teeny tiny fraction of that energy from the sun, and that's all the energy human beings have ever used for all time, except for like a little bit of geothermal and stuff. So it's an immense amount of energy coming off the sun. It's a whole big amount of change in mass. And also, keep in mind, the sun has been burning for 5 billion years or so. And even with all that, hasn't changed its mass by that much because the sun is really big. All right. That amounts to about 3 or 4 times 10 to the 26 joules every second of energy. Lots of energy. All right, so that's fusion. Of course, because you get so much energy out of fusion, it would be really great if we could harness this power on Earth. Part of the issue is that you need about the mass of the sun to have a sustained fusion reaction like the sun has. And the mass of the sun is like way more than all the mass we have on Earth. So it's really hard to do this. The joke has been for, 50 years ago, um, we were 50 years away from fusion happening. So we've been 50 years away from fusion for the last 50 years or more. It just keeps getting harder. So there have been some really brief fusion reactions that can happen. They do all kinds of crazy stuff like using magnetic fields and superheated to suspend the superheated plasma that's required to make a fusion reaction happen. You need to get stuff really, 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 really hot, um, like incredibly hot. And so we've done it to some extent, but not self-sustained fusion reactions. And at the current moment, it costs way more energy to make this fusion reaction happen than we can actually get out of it. So it's very hard. There's a lot of hurdles to overcome. Um, there's always little bits of progress being made, but again, it keeps seeming like it's maybe not too far down the line, but then it keeps staying pretty far down the line. So we will see. It's very, very much an active field of research and interest because, of course, if we can harness fusion energy, the amount of energy that you could get out of fusion is crazy. You would solve all of the world's energy problems for sure if you can make fusion energy happen. So it's in the works. It's been in the works for a long time. It is complicated for many, many reasons, which we won't go into all of them here. But that's the basic idea. Fusion would be great. We're working on it. Hopefully we'll get there at some point relatively soon. All right, let's look at the other side of the graph, though, which is nuclear fission. Because if you're noticing, there's a peak on this graph around the middle-ish, left of middle at iron. What I said was if you go up on this graph, you will get energy out. So I can fuse hydrogens into helium and get a ton of energy out. I go way up on the graph. I couldn't, though, if I tried to take an iron and smash it into another iron, I could do it. It can be done. And I would go up to, I don't know, 56 plus 56. So I would smash them together and end up somewhere here. But notice then I'm going down on the graph, which means I would be, let's see, I would be increasing mass, which would require energy because I'd be decreasing binding energy. So it'd be increasing mass. So it would actually require energy. I need to put energy into that reaction for it to happen. So it's not going to naturally happen. But I can move the other way. So fission is the opposite of fusion. Fusion is smashing two things together to get energy, which happens on the left side of the graph. Fission is the breaking apart of a nucleus into smaller pieces, which will release energy as well. So a large element that splits into two smaller ones, large nucleus, we should probably say, that splits into two smaller ones will release the difference in binding energy. Common example, there's a lot, but common example is uranium. Uranium is a big one that uranium can split. We can split the uranium atom into two smaller chunks. And as we move up on the graph here to the two smaller chunks, energy is released in that reaction. All right? So energy is released here, just like energy is released when smashing two stuff together. Go up on the graph, energy comes out. So here's a common one to know, and we can look at some nuclear reaction writing here. So here's a fun one. Uranium-235 is a very important isotope of uranium that if you bombard it with a neutron, if you hit uranium-235 with a neutron, it turns into uranium-236, which very quickly decays into these two other nuclei and 3 neutrons. So the fun thing about this is 3 neutrons come off. So for one, this will release energy because, again, as the uranium splits into 2 smaller nuclei, the total mass on the right side here will be less than the total mass on the right side, on the left side, which means the difference in mass will come out as energy. And this particular reaction is a handy one because it takes 1 neutron to start it, and as a result, 3 neutrons come off. Well, if I got more uranium-235 hanging over here, guess what? I can start 3 reactions here. And this is what we call a nuclear chain reaction. So if you have enough uranium-235, a critical mass, let's say, you can get a chain reaction to happen, which would be something like this. Those 3 neutrons can go off and start 3 new reactions. And then these 3 uraniums split, form 9 neutrons. Those can form 9 reactions, and you can see the exponential nature of what would happen here. So that is a exponential release of nuclear energy that can be great or dangerous. And this is the key behind what we use for nuclear power and also what we use for nuclear weapons. That chain reaction, if left unattended, can have disastrous results of a ton of energy being released all at once. But of course, if you can control the reaction, you can get a whole lot of energy out. So controlling that nuclear reaction is really important, and that's what we do in a nuclear power plant. There's two important pieces of a nuclear power plant. You might remember a little bit of these from studying energy sources, but you want to make sure you know these. These are two important ones that they ask about all the time. So it's all about the neutrons. There's first a moderator, and honestly, a moderator is typically just water. All of this is happening submerged in water. Sometimes other stuff, but often water. So moderator is just something that slows the neutrons down. As they come off, it slows them down for reasons we don't have to get into, fun quantum stuff. The neutrons have to be moving relatively slowly to interact with the uranium-235 for the reaction to happen in the first place. If they're moving too fast, there's basically not enough time for them to grab onto each other. So the moderator slows them down so that they can start new reactions, because the neutrons that come out of the reaction, the 3 neutrons, are pretty fast. So the moderator will slow them down, and then control rods are a really key part. Control rods are actual rods that are put into the reaction vessel, which can absorb neutrons. They can absorb extra neutrons, so that you don't get exponential release of energy. So you can control the rate with that. So here's sort of the idea of what's happening inside of a nuclear reactor. So there's a vessel, there's control rods in here, and you can bring the control rods down further, where they'll absorb more neutrons, or you can pull them out further, where they'll absorb less neutrons. You can control the rate of the reaction with those control rods. That's the idea. And guess what? This crazy nuclear reaction that we're doing, where you're splitting the atom to release the difference in mass as energy, guess what we use it for? Well, that energy is kinetic energy of stuff all flying around. So we use that kinetic energy to heat up some water and make steam and turn a turbine. All right. So even with something as crazy as nuclear power, we're really just making energy to make heat, to heat up water and make some steam and turn a turbine with it. There you go. And of course, we can use that turbine, spin a little generator. That generator spins around. You got a changing flux situation for my HLers. The changing flux gives us a induced magnetic field. We can do all kinds of fun stuff then by creating alternating current, send it along, transform it up and down to send it for use. So you can plug in your computer and watch this fun video. All right, so that's the idea of a nuclear reactor. Do know about the control rods and the moderator. Okay, so let's just do one example with fission. When you write these reactions, we've been doing this a little bit, but let's formalize it here. There's 2 numbers that we write with every symbol for an element or a nucleus is usually what we're talking about here. So the number at the top left is the nucleon number. That's protons plus neutrons. And the bottom left is officially the charge, which you can more or less, for most stuff, think of as the number of protons. So uranium nucleus, uranium-235, has 92 protons. So it's got a charge of plus 92. That's in terms of the elementary charge. So that's not coulombs, of course, right? That's 92 elementary charges, because each proton has that much charge. So it's got a charge of 92. So there's 92 protons, and there's 235 total protons and neutrons. So if you need the number of neutrons, you subtract, yeah? 235 minus 92 is how many neutrons are in this big old nucleus. All right. So the thing with nuclear reactions is these are super easy to do. You will often be asked to balance them, and all you do is the top numbers have to balance and the bottom numbers have to balance. All right, charge is conserved in every single nuclear reaction. So however much charge you start with is however much charge you have to end up with. And so is the nucleon number, it turns out. Even when crazy stuff happens, like protons turning into neutrons and vice versa and all weird stuff, the total number of protons and neutrons will be conserved on the left and right side of a reaction. So you can use coefficients in front, so just watch out for that. So convince yourself looking at this. You know, on the left side, my total top is 236. There's 236 total nucleons to start. Whoops. And at the end, I still have 236. Add these up and do 2 times 1, you get 236. And then same deal, I have a charge of 92 at the beginning because the neutron has no charge. At the end, I do still have a charge of 92. I got to add 42 and 57 and then subtract 7 because there's 7 electrons, and each electron has a charge of -1 elementary charge. All right, the little e means electron, little n means neutron. If you see a little p, that's a proton. That's the idea. All right, so nuclear reactions are pretty easy. Just balance the top numbers, balance the bottom numbers, you're good to go. The IB might ask you to fill in like missing numbers, that kind of thing. We'll practice some of those. Okay, here's one to practice right now. Here are some masses and information about this classic nuclear reactor equation where we're making molybdenum and lanthanum and some neutrons and electrons. So you will need the front of your data booklet in addition to these numbers here. Try to use the good old equation we used last time to figure out the change in mass, the energy released, and then see if you remember what specific energy means. So take a couple minutes, pause the video, and try this on your own. Make sure you can do it, and we'll go through it in a second. Okay, here's what you should get. You are adding the masses on either side and taking the difference. Don't forget to pull the mass of a neutron from the front of your data booklet. Double the mass of a neutron over here, 7 times the mass of an electron over here. Don't forget that one. It doesn't add much, but it adds a little bit. And when you take the difference from this side to this side, you get this in atomic mass units. So there's that many atomic mass units. You just convert that to MeV per c squared, then plug it into E equals mc squared to get 204 mega electron volts of energy. And specific energy means, think of joules per kilogram. All right, so joules per kilogram. So really, what you want to do is divide, basically turn this energy into joules, turn the mass of a uranium into kilograms, and divide them, and you'll see that you have about 83. This is a weird way to write it just because we usually do specific energy in megajoules per kilogram. You might have some more zeros than having a joules per kilogram, which is great. But it's about 84 million megajoules per kilogram, which is way, way, way more than anything else. If you remember comparing specific energies, uranium is very energy rich because we're not doing a chemical reaction, we're doing a nuclear reaction, and we're turning mass directly into energy with this reaction. So you get a lot out for just a little bit. Okay, so there you go. There are the ideas of fission and fusion for your enjoyment as we go on and do some nuclear physics together. So have fun.